Right. So this is another question on Bayes' theorem, and the problem is that let's suppose you expect to get a letter from one of two cities, right? And only one of these two cities. And the first city is Arlington, and the second city is Toronto, right? So the probability of you getting a letter from Arlington is half. Oh, and you getting the letter from Toronto is also half, right? So you're equally likely to get it from either of these two cities. And let's suppose this is the back of the envelope in which you get the letter. And the back of the envelope, the sender writes his own address, so that in case the letter cannot get delivered, then it can be shipped back to the sender. And in this address, he's written the name of the city, which could be either Arlington or Toronto, right? And but what's happened is that the letter was lying outside and probably some water fell on it, and so all the ink got washed away. And so the only two characters you can see in the sender's address are the characters O and N, which is here in Toronto and which is here in Arlington. So if the letter came from Arlington, then barring these two characters, everything else got washed away. So you can only see ON. And if it was Toronto, then other than these two characters, everything else got washed away. So the question is that if the only two characters you can see are ON, then what's the probability that the letter came from Arlington? So this is a probability that we are supposed to find. Now your first reaction, it certainly was my first reaction, would be to say that, hey, this is a trick question. I mean, the probability is the same as probability of A, which is equal to half. But as we will see, this is a conditional probability, and therefore we have to apply Bayes' theorem, and Bayes' theorem will give us a slightly different value. And you can appreciate why the value would be different if we take another example. So let's suppose it's not Arlington and Toronto that the letters come from, but Arlington and another city called ON, 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 ON. So let's suppose this is not a real city, I've just made this name up, but let's suppose these were the two cities you were expecting to get a letter from with equal probability, right? Now, if water is going to fall on the envelope, and if ink is going to get washed away, then with which of these two words do you think it's more likely that the only two characters you can now see are ON, right? So if only two characters are going to survive, then with which of these two words do you think those characters would be ON? Well, Arlington has just one ON pair, but this other name has 4 ON pairs. And so my guess would be that it would be this name with which I'm more likely to see ON, right? So here's an example. It's a make-believe example, but here's an example where which tells us that the answer cannot be as simple as just half, right? So what we need to do is actually apply Bayes' theorem. And what Bayes' theorem tells us is that the probability of the letter having come from Arlington, given that the only two characters you can see are ON, is equal to the probability of ON given A into probability of A divided by the probability of ON given A into probability of A plus probability of ON given T into probability of T. So T is the event that the letter comes from Toronto. Now, in this expression on the right, so this is just an expansion of the Bayes formula, right? And in this expression, we actually really don't know much. We know PA and PT. We know these because we wrote them down over here. Let me go back up, right? These were half, so we wrote those down. So we wrote them over here. So that's simple. But other than that, the terms that we absolutely have no idea about are PON given A and PON given T. These are the tricky terms, and we have absolutely no idea what they are. So let's see how we can find these out. So let me just write down Arlington again. And this time I'm just going to write the characters a little far apart, right? So this is Arlington. And let's suppose you have a cover, right? So this is a cover. It covers 2 characters at a time, only 2 characters at a time. And you place this cover on the word, and then you pour water on everything else so that everything else gets washed away. So if you place this cover starting at the first character so that it covers the characters A and R, then and then pour water, then the only 2 characters you will see afterwards are A and R, because that's what the cover was on. But you can do something different. You can take this cover and move it 1 character to the right. So you can move 1 character to the right, in which case it covers R and L and nothing else. And so then you pour water again, and the A gets washed away and everything else gets washed away, and you're left with R and L. Then you can move it 1 more character to the right, in which case it covers L and I, and everything else gets washed away. So you're left with the characters L and I. So you can keep on shifting this cover 1 character at a time to the right. And the last position for this cover would be starting at the second last character and ending at the last character, so that you get an O and an N, right? So you can only shift this cover n minus 1 times. So if the word is n characters long, then you can shift it n minus 1 times, so that the last position actually starts with the second last character, right? So that's kind of the insight. I'm just trying to move this down. Yeah. So the insight is that if a word is n characters long, then it has n minus 1 pairs. You know, these pairs over here, then there are n minus 1 such pairs. So Arlington has 9 characters. So Arlington has 9 characters, which implies it has 8 such pairs, right? And ON is just one of them. And Toronto is 7 characters long, which implies it has 6 such pairs, right? So the probability of ON given A is actually, so we have 8 possible pairs and ON is just one of them, right? And implicit in this is the fact that we really can't change the order of the characters because Arlington has a specific spelling, right? So this is not a question about in how many ways can you pick 2 characters from 9 characters. This is not that question. You cannot change the order of the characters. So we have 8 possible pairs and ON is just one of them. And similarly, let me just see if I can go down a little more. And similarly, Pn of ON given T, so if it's Toronto, well, Toronto has 6 possible pairs and ON is just one of them. So now we have values for these tricky probabilities that we were looking for. And so now it's just a simple question of plugging these values into into the Bayes theorem. So if we do that now, I'll just section out an area. So that would be PA given ON would actually be equal to PON given A into probability of A divided by PON given A into probability of A plus PON given T into probability of T. So this is equal to 1 by 8 multiplied by 1 by half, right, divided by 1 by 8 into 1 by half plus 1 by 6 into 1 by half. Now the 1/2s cancel, we can take them out, they bring nothing to the table. So what we are left with is 1 by 8 divided by 1 by 8 plus 1 by 6. And if you do this calculation, and you can do this on your own, you can try this on your own, it's very simple, it would be 3 by 7. So the answer to our question, I'm getting a cell phone call. So the answer to this question, that the letter came from Arlington, given that the only 2 characters you can see are ON, is 3 by 7. Now this was a tricky problem, so if you need to see the solution again, then do that, you know, because it is a little much to digest. But this is also a great problem because this is the kind of problem that tells you that using your intuition as a guide in solving probability problems is not a very good idea, and that probability has a way of surprising you. So this is a great question to understand that.